Let's look at another algorithm that's used to generate the minimum spanning tree. In the last video, we looked at Kruskal's algorithm, and Kruskal's algorithm basically just picks the edges of minimum weight. So, we might pick the 1 and they might pick the 2 here, and basically it just picks edges from all over the place, and it actually starts to build a network that might appear a little bit disorderly at first and all disconnected and disjointed, but eventually all comes together nicely in the end to form our minimum spanning tree. So it's possible then to get from any vertex to any vertex. So you can think of Kruskal's algorithm as a little bit disorderly and a little bit haphazard in that it just picks edges from all over the place. Sometimes though, we want to build a minimum spanning tree where the tree actually grows as if it's growing from the roots all the way to the top, and there's nothing disjointed, so you don't have an edge here or an edge there or an edge here, but it actually grows the edges basically from a source or from a starting point until it eventually all the edges basically connect everything up. And that's sometimes the algorithm that's used, for example, to build internet networks, for example, electricity networks. It kind of doesn't make sense to put a wire from, say, B to D. I might just draw it in there, and then say from F to E, but the generator's at A. It is counterintuitive, isn't it? It sort of doesn't make sense. It makes more sense though that from wherever the generator might be, you start to grow the network from the source. Okay, so it's also for traffic as well. So let's just say that there's a major city and we want to connect that major city to some regional towns. It probably makes sense to build the road from the major city first and then slowly start building it out until it eventually encompasses all the towns, okay, that are there. So let's have a look at Prim's algorithm. So Prim's algorithm, okay, like I said, it's a bit more orderly. We need to pick a starting vertex, and it doesn't really matter which one you choose. You choose any one you like. In the end, we're going to build a minimum spanning tree. A tree means that every one of these vertices have to be connected eventually. So pick whichever one you like. And we can start from, I don't know, let's just start from A, because we can. And A is the first letter of the alphabet, so I might as well start there. So the way it works is this. We pick our start. Okay, so let's say we're starting here at A. Okay, so we're going to start at this vertex here. So it works by vertices, not so much by edges as Kruskal's algorithm does. Starting at A, let's have a look and see what edges join to A or connect to A. We have this edge here, AF, which is worth 4. We got AE, which is also worth 4. AC is worth 8. AD is worth 6. AB is worth 3. You pick the smallest. Okay, so like Kruskal's, we still got to pick the smallest or the lowest weight edge or the lowest cost edge. Okay, so let's say we're building a road network. We pick the lowest cost. So starting from A, the lowest cost edge is 3. Okay, and we might as well, so we're putting the weight there and sort of start to build our tree. Now what we do is from A and also from B, okay, we're going to start building our tree now from one of those two vertices. Because now we've connected A and B together, we can't connect E and D now. Whatever we start to draw has to build on the original tree that we've started. We've started the tree here. The next edge we draw has to come from either A or B. Okay? It's very important that as we build our network, it must remain connected all the way through. That is the reason why we use Prim's algorithm over Kruskal's algorithm. If you ever get a question that states, why would you use one algorithm over another? They're not just two random algorithms or just two things that work. There is a reason why we would choose Kruskal's. There is a reason why we would choose Prim's algorithm. That is very, very important. Okay, back to this. From A, okay, what other edges have we got? We got a 4, we got a 4, we got an 8, we got a 6. Okay, you could list these down somewhere if you like. It's up to you how you want to do the accounting for this, or you can do it by inspection. That's fine. Now from B, we have a 7. Okay, we've got a 9, we've got a 6, we've got a 2. Out of that set of edges, or that group of edges I just called out, BD would be the smallest. Okay, so let's put that in. Okay, and that's a 2. Okay, now the next edge that we're going to select has to either connect to A, has to connect to B, or D. Okay, again, we're building our tree. Again, Kruskal's probably not very happy here, going, oh, hang on a moment, but there's a smaller edge out here somewhere. No, that's a different algorithm. Prim saying, no, we've got to maintain the tree, okay, and maintain the connectedness of the tree. Must remain connected as we join on these roads, okay, or these edges. All right. So, from A, what edges have we got? We've still got the 4, we've still got the 4, still got the 8, we've still got the 6. Now, we can't choose the 6 because that obviously it's bigger than what other choices we've got. Plus, it forms a cycle, so that sort of rules that one out now. So we can't actually... The 6 is actually gone because it forms a cycle if we join that. From B, we've got a 7, we've got a 9, we've got a 6. Now, the 2 is already taken up. Okay, so... Now, from D, we've got a 6, we've got an 8, we've got a 5. Okay, so I think the one that we're going to use this one here, the A, which is the 4. Okay, which is going to connect up to vertex E. Okay, sometimes, or there's another 4 here that we can use as well. Actually, we have two choices. We've got AE or AF. It doesn't really matter. In fact, you may end up with a different shape minimum spanning tree from the last example that we did with Kruskal's, but the minimum weight should still be 12, and that's what we got in the last example. So let's compare. Okay, which one do you want to choose? Doesn't really matter. I think maybe we'll just connect A, E together. How's that? All right, so we'll do that. Okay, and that's worth 4. Okay, right. So far, what's the weight of this network? 2 plus 3 is 5, 5 plus 4 is 9. All right. Now, we've got more choices. We need to choose 2 more edges, okay? So we need to connect F and C somehow, okay? Now, from E, we can see that there's an obvious choice. We've got a 1 here. Okay, there's no other 1s anywhere else. So from E to C, that is the obvious choice. Okay, and that's a 1. Notice that every edge that I've chosen, that we've chosen so far, every edge that's chosen has built the tree and has maintained it in a connected state. In other words, as we're building a road, it connects all the other roads with it, not all separate, disjointed all over the place, and then finally the final road goes in that then sort of connects the whole thing together. All right, we've got one more edge to choose. Okay, again, looking at all the choices that we have, and Prim's takes a little bit more time because you have to consider all the different options. And as you start to build these roads, you have to start thinking, well, what's the smallest edge I can choose that connects to all of these vertices? Because you have to consider all the edges that come off all the vertices that we've connected so far. Now, we do have a fairly obvious choice here. Okay, we've got FC, which is a 2. There was another 2 somewhere else, which is BD, which we've already chosen that one, so we can't pick that again. That's useless. But connecting F, we've got AF, which is 4. We've got FE, which is 3. We've also got FC, which is 2. Now, I could just build it. I could just put it straight across. In fact, I might just do that, or I could sort of draw it around. In fact, how about I do that? Okay, you can. Doesn't change the network at all. It's still worth 2. Okay, or I could have just drawn it across. Doesn't really matter. Okay, right. Let's see if we got the minimum weight of 12. Okay, let's add up all the weights. So the minimum weight of this network. Okay. Okay, of this spanning tree is equal to, what have we got? 1 plus 2 plus 2. So what's that? That's 5 plus 3 plus 4. That'll be equal to 12. So we end up getting the same weight as the example that we did using Kruskal's algorithm. In fact, we ended up even getting a different shaped network. Okay, so the different roads that we've built, we've actually chosen some, maybe I think we've chosen 1 or 2 different edges, but we end up still with the minimum weight. In other words, the cost of building this network is exactly the same as building the network that was determined using Kruskal's algorithm. Okay, And that's how Prim's algorithm works. So always remember, and I think probably the take-home point from here is, why would you choose one algorithm over another? Okay, Kruskal's is less complicated, but it tends to be a bit more haphazard. It does not maintain the connectedness of a network as you build it. Prim's, on the other hand, does. So Prim certainly does have an advantage over Kruskal's just in that point alone.